Good morning, Kyle. How are you?
I'm doing well, Nick. How about yourself?
Very well. Last day of classes. The little things. Okay.
Hey, Nick.
Yep.
I have a question about the homework.
Sure.
So for 10.8, we're supposed to calculate and simplify the weakest precondition.
Yes. That is on my list of things to talk about today
Okay.
because I've gotten several questions about it. But go ahead and ask, and we've got like 7 minutes, so fire away.
So using the example given on page 185 at the bottom,
Okay.
I went through a similar process using textual substitution to find the precondition.
Right. And that would be the right thing to do.
So in the on the assignment page on Canvas, it says that 10.8 is basic assignment problem using 10.2. What I was wondering is how would I implement 10.2?
Oh, yeah. So maybe talking about 10.2 wasn't really in my head they're all kind of the same, but looking here at 185, it doesn't really look like 10.2 necessarily. I mean, really all you need, so if it helps to ignore my comment about 10.2 and just do what it says on 185, that's entirely reasonable because 185 is the model to use.
Okay.
And then it turns out that what they're doing on page 185 is essentially a variant of proof rule 10.2. But you're right that proof rule 10.2 is really saying prove that this is correct, and that's not exactly what this problem is about because we don't even know what this is yet. So I think if you did what it does on page 185, that's good. Don't sweat it.
Okay. Thank you.
You're very welcome.
What's your shirt today, Nick?
That's actually a Doomtree shirt. No Kings. And that's Doomtree sort of in the background at First Avenue. I hadn't actually
Cool.
intended all that to like fit together. I just pulled this shirt out of the drawer this morning. I don't pay a lot of attention to what shirt sort of comes out of the drawer as a rule.
Did you see Doomtree at First Ave?
Yeah, that I took that picture.
Nice, cool.
Our son and I went and saw their blowouts several years in a row back in the must be in the early 90s. I mean early 2000s. So yeah.
That must have been wild. I can only imagine.
It was really good. It was really
yeah,
good.
I bet.
One of them. So these were always in December, and there was one year where, so we had tickets for a Saturday show. Yeah. And my wife called at, I don't know, 3 in the afternoon, called up to school and said, the weather says there's this terrible storm coming in. If you and Thomas are going to get to the cities, you probably have to leave now. And I was like, oh, okay. So
This was in December?
yeah. And so we got in the car and we just took off and stayed at a hotel that night, and it snowed like a ton. I mean, over a foot of snow. It was really a mess. And so it was a thin audience. Like they had probably maybe half the audience. I mean, they'd sold the place out, but so many people just couldn't get there. And so it was a really interesting show because it was, a much smaller audience than you would have expected. And I don't think that's this year. I think this is a different year behind me. But it was interesting being there when so many people hadn't been able to make it. And like one of the band members, it had taken him over an hour to get from his house to the club.
Oh man, I'm jealous. That would have been a crazy cool show.
It would have been. It was. We had a great time. So.
Oh man.
Sorry. Yeah, if we didn't live so far from the cities, I'd go to a lot more shows. But
it's hard. It's hard to get there. Well, especially now. There ain't no shows going on.
Well, right. I mean, now there's nothing. So nobody's going to shows.
I saw Mindless Self-Indulgence at First Ave, and they were great.
Very cool. Very cool. Our son lives in Minneapolis now, and so he's able to go to a lot more stuff than I can. But
oh, gotcha.
Sigh.
Actually, I haven't been to any shows lately. The last show I saw was Red Hot Chili Peppers at the XL Energy Center, and that was
wow.
That was so long. I feel like that was so long ago. 5 years ago.
I went to a show in the cities in September last year at the Cedar. It was really good. But well, we should start because it's 9:15. And it's the last day of classes. Oh my God! Whoa!
Oh.
So it's amazing. We've all survived. How did that happen? So I don't. My plans for today are to first talk about. There's some things patterns that have come up in questions about Chapter 10 exercises. And I want to talk about a couple of those things, and then any other questions that people have about homework or exams. And then if there's any time, we can talk some about proving the correctness of loops. If there's not, it's fine. And I kind of assume if there's a few questions on top of the stuff that I've got on my list, we're probably not going to get there. And that's good. We'll just let that go. There have been a number of questions about the problems 10.8 and 10.11. And one question about 10.8 that just got asked before class started got me thinking that I may have actually said something that wasn't wrong, but might have been misleading and unhelpful, in which case I apologize. So I'll try to clean that up a little bit. And then there was a question about skip that I thought might be worth coming back to. And then any other questions the audience might have as we wrap up. So a reminder, got buckets of sign-up slots Monday, Tuesday, Wednesday. And the exam is then due Wednesday night. So start early and ask lots of questions. So any sort of big picture questions before I start talking about some of this Chapter 10 stuff? Okay. I'll go for it.
Is the what would you say is because you've been lenient when it comes to late assignments, when would you say is the final
the absolute cutoff?
Yeah.
Well, I mean, anything I get, if I get stuff by the middle of next week, I'm probably okay. I'll probably have time to grade it, right? That's the real issue, is if everything showed up like 5 minutes before grades were due, I just wouldn't be able to get it all done. Increasingly, I'm doing this all myself because the TAs have just been swamped by being away and everything. So, if you got stuff to me by middle of finals week, I think we could deal with it. After that, it starts to become less obvious whether I would have time to get to it. So does that make sense? Does that seem reasonable?
Yes, thank you.
Okay, good question. And I do want to try to be as flexible as I can. I know it's been difficult for a whole host of reasons for different people. So, if I can help out, definitely let me know. Okie dokie. Anything else before we actually start doing chapter 10 stuff?
Just double checking. So this weekend, like, are you going to be like available on Slack to like answer messages as kind of?
I will probably be around on Slack and email at least some this weekend. I don't make any promises on exactly when and how much. I've got a combination of a bunch of grading I'm going to try to get done, including some for you folks, and some family stuff to deal with this weekend. So, like, don't expect to hear back instantly necessarily, but you're certainly more than welcome to ask questions. And if I get to them, I get to them, I think is going to be how that kind of goes. The other thing, just as a heads up, I tend to go to bed on the early side for, compared to most of you crazy youngins. And so, if you ask questions in the evening, well, you might not get an answer back till the next morning. And I'll still try to answer it, but I'm, I don't tend to be like camped on Slack 24/7. But I totally feel free to send me stuff over the weekend and I will get to it when I can. So does that make sense?
Yep.
Cool. Other questions? Okay, then let's actually talk a little bit about exercise 10.8. So whiteboard. Get you up out of the way. Get you up out of the way. Oh, go away. Okay. So 10.8, exercise 10.8. Is you have question mark, and then you have a whole sequence of assignments. X gets some stuff, and then Y gets some stuff. And I'm not going to repeat all the stuff here. X gets some stuff. And then our post condition is X equals big X, which is a rigid variable. So I've been doing those in brown earlier. And Y equals big Y. That's a rigid variable. Okay. And I said something in the write-up about this being sort of like that you would just use proof rule 10.2. And a question right before class actually pointed out that that's actually a little misleading, because really 10.2 has a precondition here and says, like, if you have a precondition and an assignment how do you show that the precondition followed by the assignment leads to the postcondition? Well, we don't even have a precondition at this point. And so in some ways, the better model for what to do with this would be the example on page 185. 185 is definitely useful here. It's the sort of model to follow probably. But the basic idea, these problems that have question marks at the beginning, what we're looking for, if we don't know the precondition, we've got a program. Let's just do a real simple thing. So this is saying, under what conditions as a precondition would it be the case that if we start with the thing that we're trying to figure out, and then we add 1 to x, we end up with x equals 7, as a very simple example. And the solution to these, and this is, we're looking for what's called the weakest precondition. Because we could always have all kinds of random things in the precondition. We could be like, blah, 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 and this ball is red, and it happens to be Friday, and it's sunny outside. We have a lot of stuff in the precondition that isn't necessary. So we're often looking for the weakest precondition. What's the simplest, smallest thing that is enough to get us to x equals 7 as the postcondition? And we can compute the weakest precondition by just taking the postcondition, x equals 7, and applying the assignment as a substitution. So by textual substitution, we would get that x plus 1 is 7, and then we do a little algebra, and we get x equals 6. And so that's our weakest precondition. That we must know that x is 6 here, and if x is 6 and we do this, we'll get to 7. We could know more than x equals 6, but the minimum that we have to have is that x is equal to 6, okay? And if we have multiple assignments, let's say we've got question mark and we have x gets, let's do x plus 1, followed by x gets x times 2. And let's say that the postcondition is x equals 10. So to find the precondition, again, we just take the postcondition, x equals 10, and we do the assignments as substitutions. But, and this is the thing that often messes people up, it's crucial that we do them in reverse order. So we have to do the last one, then the one before it, then the one before it. So in this case, you have to do this substitution first, then this substitution, then this substitution. You can't do them in the other order, it won't work. So we would do x gets x times 2, followed by x gets x plus 1, and that is by textual substitution. So I'll just do this substitution here first. So we get x times 2 equals 10. And then we still have this substitution left to do. Okay. And now we just keep going, grind through the substitutions. Actually, I should point out, it's okay to actually do a little simplification here if you want to. Like, you could first do all the substitutions and then simplify, but it's okay to simplify as you go. So I'll actually do that here. I'll do a little algebra here. And then I've got x equals 10 or 5. Wow. So I'm just dividing through by 2 on both sides. And then, and is that still visible down here at the bottom? Because I know we had a problem once with that. Okay, cool. Thank you. So I'm going to rewrite that 5 because that 5 was terrible. Okay. So then we'll do textual substitution again because textual substitution is such fun. And then we get x plus 1 equals 5. And then by a little algebra, we get x is 4. So this tells us that the weakest precondition here that goes where this question mark is that x is 4. So that if x is 4 and we add 1 to it, that would make it 5. And then we double it and that would make it 10. So that gets us to here. So we have to have that x equals 4 would be part of the precondition. There could be more stuff, but it's got to have at least x equals 4. And so that would be the solution to the question mark. And that's how you would do this exercise 10.8 is you would take this and you would just go through the substitutions backwards, do this one, then do this one, then do this one. And the result of all of that is going to be what you put in for the question mark. Okay.
So is there a way to verify that your precondition is correct?
Yeah, great question. Essentially, if you start with, in this case, if we start with x equals 4 after we've solved for it, and we just go back through, you should get the postcondition, right? You should get this. So if we start with x is 4, and then we add 1 to that, well, then x is 5, and then we double that, x is 10. Oh, that matches the postcondition. Life is good, right? As an example of where you could get into trouble on this and where a check like that would be a good idea is if I'm going to erase this little bit here. Because I want to save the bit at the bottom so that we have that solution. And then I'll do an incorrect one in red here. So this is sort of a broken version. Undo. There we go. A broken version of this here, where let's imagine I forget to do them in reverse order and I do them in sort of left to right instead of right to left. Then I would have x equals 10. And I would do if I do the substitutions in the wrong order, then I'm going to get x plus 1 equals 10. X gets x times 2. And this is going to be x equals 9. And then I still got the substitution, x gets x times 2. And now I've got x times 2 equals 9. And that is x equals 4.5. Okay. So if I've done them in the wrong order, I get x equals 4.5. But if I kind of go back through with that, I'm going to realize something's wrong. Because if I start with 4.5 and I add 1, I'm going to get 5.5. And I double that, I'm going to get 11. And that's not my desired post condition. So yes, you ought to be able to take whatever you get down here and then run it forward through the assignments. And if you don't get this at the end, you should be at least suspicious. Does that make sense? Does that help?
Yes, it does. Thank you.
Cool. So I think that's all I was going to say about 10.8. I've got something I want to say about 10.11, which is the Fibonacci assignment problem and solving for E and F. But are there questions about this before we go on to that? Okay. Then on exercise 10.11, I guess I should switch back to black here. You have this situation where you're trying to, you've got P followed by this assignment, NAB gets N plus 1, E and F. And you want to get back to P, where P is N at least 0, or N greater than 0, sorry, and N equals, oh, not N, A equals F of N, where F is the Fibonacci numbers again, and B equals F of N minus 1. So you're looking for, so we want to solve for E and F. We want to find expressions for E and F that make this true. And one thing that's not, I think, super clear necessarily in the write-up is you want those expressions to not include references to big F. So initially, when you do the substitutions, and this is 10.2 stuff, if you do the substitutions, you're going to have E equals something with F's in it and a big F, Fibonacci's in it, and F will have Fibonacci's in it. And your goal is to get rid of those, to do some math that makes those go away. And that's where your precondition is useful, because your precondition tells you that F of N is A. So if you ever see F of N somewhere, then you can replace it with A. You're trying to replace the Fibonacci bits with program variables, in particular with A or B. And so if you see an F of N, replace it with A. If you see an F of N plus 1, replace it with B, because you know that A is F of N and B is F of N minus 1. If you see an F of N plus 1, well, you don't have something about F of N plus 1 here. But if you use the Fibonacci rules, you can rewrite F of N plus 1 in terms of things that you do know stuff about, and then you can simplify from there. So, and I'm being a little vague because it's sort of walking a fine line between giving you a hint and just telling you what the answer is. But your answer should be, E is something that's got like A and or B in it, and F has, something with A and or B. You might not need both A and B in both of them, but not, don't include big Fs. In your answer. And again, you ought to be able to, in some way, check your work, because you could say, well, if we start knowing all of this and I do this assignment, is it true that P is going to be true again? Like after I've done the assignment, can I check that the state of N, A, and B satisfies all of these conditions? And if that's true, then you're like, woo, yay team, did a good thing. If it's not true, that sounds like a good time for a question. So, questions about any of this chapter, either of these chapter 10 problems? And then I was going to say one last thing about skip, and then we'll see if there are other questions. So skip comes up in one of the exercises, and if you have Q skip R, that's correct if Q implies R. That's all you need to do there. So the proof rule for skip, which is, the book kind of buries it in a footnote on page 188, and then doesn't really sort of give you a proof rule like this. But this is the proof rule for skip, is that if you have a precondition, skip, a postcondition, that's valid if the precondition implies the postcondition. Since skip doesn't do anything, if our goal is to get R to be true, it must be the case that Q makes R true without any other changes happening, because skip does nothing. So basically we're just saying this Q gets us to R without any other action, because there is no other action implied by this little program. So that's all you have to do for the skip part. Questions about that?
So we're supposed to prove that Q implies R for
Yeah.
R? That's all?
That's all.
All right.
So if you find yourself with one of your sub goals is something, skip something, all you have to do to show that this works is to prove that Q implies R, and then you're done. And Q implies R ought to be pretty easy. It should be fairly straightforward to show that Q implies R in the problem that you're working on. So that's all you need to do there.
Okay.
Questions? So that's it for my notes that I was going to talk about today. I'm happy to take any or all other questions that people might have. If there aren't any, then I will run to section 12.6 and we'll quickly sketch out what's involved in proving the correctness of loops, which isn't necessary for any of the homework or the final, but might help explain where the last 3 problems on the final come from. So are there any other questions about anything? Sorry.
On the final for problem 2, when it says Ted claims, is that an implication statement or
No, it's Ted says.
Ted
So
says
it's
okay.
still Ted equivals. So Ted claiming is the same as Ted saying in this case.
Okay.
So it's still just an equivals like all the other times.
Okay. Thank you.
No problem. Other questions?
I guess I have a question that relates to the last couple problems, I guess.
Okay.
So I just have a question. So like, especially with like the three conjuncts and that implies something. I have a lot of English in that, and I guess like I'm wondering about like the formal process. Like this is gonna be a crude example, but if I have like object dot fruit and object dot yellow and object dot not any other yellow fruit implies banana, like those three conjuncts like obviously imply the banana, but I don't know how to explain that without just writing about a ton of English. I guess, do you know the nature of my question?
So let me write something and you tell me if I'm getting the right idea. So are you saying you have something like P and Q and R implies W? Is this the sort of structure that you're talking about?
Yeah.
And is the concern that like one of these like gives you W pretty easily, and the others aren't necessary? Is that the sort of thing or?
I mean, yeah, that's also something that comes up, but like even just like explaining that, like I just have like follows from and then a paragraph about why that's
Oh,
true.
no, and that's probably a bad sign, right? If you find yourself writing a paragraph of English, that's, probably missing the point somewhere. So let me see if I can come up with an example and tell me if this example captures in some way the concerns that you have. So let's say that we have X greater than 0 and Y greater than 0 and X plus Y less than 10 implies Y at least 0. Supposed to be an implies. Is that, if we talk about this example, is that helping answer the question that you're trying to ask?
Yeah.
Said hesitantly, like maybe I could make the example better. Is there a way we could change the example where it would fit the kind of thing you're concerned about more accurately?
I guess I would need to see where you go from here.
Okay, well let's do this and then let me know. So I would say here, because I don't want to write all this out over and over again, I would say let's assume the left-hand side. I.e. X is greater than 0 and Y is greater than 0 and X plus Y less than 10. Then Y at least 0 equivals Y greater than 0 or Y equal to 0 by sort of definition of less than or equal to, right, or greater than or equal to. And then this follows from Y greater than 0 by 376A, which says that thing implies thing or thing. And then this is true by assumption. Because this, right, that assumption exactly matches this. And I'm like, woo, I'm done. Did that in any way assist?
Yeah, I just thought you had to prove it that it follows from all three of the conjuncts.
No, no, no. You don't need to use them all. You just use the ones you need, right? This is saying this is all stuff you know. That doesn't mean all those things are things that you need to know to do what you're trying to do, right? You know a lot of things that have nothing to do with this class, but it doesn't mean you need to use them all to do the final, right? We frequently know way more than is strictly necessary to do the thing that's right in front of us. And when we get into the more complicated proofs of things like proving the correctness of loops, we often end up with a lot of stuff, and we don't need all of it all the time. That's actually a pretty common situation, is that we might have several pieces in our left-hand side, but we didn't need them all for this particular piece of the right-hand side. And a place where this comes up a lot is if you have something like P and Q and R implies W and X. Well, we can assume P, Q, R, and then we can break this down into two pieces. So we could prove W, and we can prove X as two separate proofs. And it's entirely possible, in fact, highly likely, that we don't need all three of these for both of these proofs. Excuse me. Hay fever, allergies. So we might have that we need P and Q to prove that W is true, and Q and R to prove that X is true, or maybe just R to prove that X is true, or maybe all three of them to prove that X is true. Who knows, right? I mean, it can vary from problem to problem, but it's very possible that when we have multiple conjuncts on the left and multiple conjuncts on the right, that you don't need all of these to prove every one of these separately. You might need all of them eventually to prove the whole set, but you don't need all of them to prove individual pieces of the set. Does that make sense? Does that help?
Yeah, that makes sense, and it helps.
Cool. Other questions?
So does assuming the left hand side work with Q skip R?
Yeah, totally. Because you're just trying to prove Q implies R. You can assume Q and then prove R. That'd be totally fine.
Okay.
I mean, essentially, anytime you have an implication, you can assume the left-hand side and then prove the right-hand side. That's that proof rule from chapter 4. If the left-hand side is a conjunction, you can kind of assume them as separate pieces as a way of cutting down on the baggage for things like this. If the right-hand side is a conjunction, it's acceptable to prove them as separate parts as long as you prove them all, right? If you'd rather not have to carry all of this around all of the time, you can prove W and you can prove X, and then you're good.
Okay. Thank you.
You're very welcome. Other questions? Awesome questions today. Thank you. Going. Gone. Okay. So we're going to do a real quick spin through what it means to prove the correctness of a loop, which means we'll have to talk for a second about what a loop actually is in this context. So the book uses a thing called do, which is essentially the same as a while loop in most programming languages. So if you've done some programming in Python or Java or something like that, you may well have run into a while loop. What the book calls a do is the same as those while loops. If you haven't seen that anywhere, that's fine. And the idea is pretty simple. So the book has do B arrow S odd. And the OD here is just backwards do. It's a way of saying we're done with the loop. So in most modern programming languages, this would look something more like while B open curly brace S close curly brace, or something like that. So they would have some sort of markers indicating the beginning and end of the loop that are usually punctuation marks. In the book, they just use this do odd thing. And what this means is we see if B is true. If not, we're done. So we don't do anything. Let's see, if not. If true, then do S, and then go back and start the loop over again. I.e., go back up here, see if B is still true. If it's not, we're done. If it is still true, do S again, back to the top, see if B is true. If it's not, we're done. Otherwise, do S again, back to the top. So we're going to do something over and over again as long as B is true. And a sort of simple real life example, you might have something like do there are dirty dishes in the sink. Arrow, pick up a dish and wash it. Wash it and put it in the drying rack. So here, we're standing in front of the sink. We look in the sink. Are there any dirty dishes? The answer is no, then we're done, right? No more dishes to be done. We can go play games or read a book or do our homework or whatever. But if there are dirty dishes in the sink, if this test is true, then we do the body of the loop. We pick up a dish, we wash it, and we put it in the drying rack. Then we go back here and we say, are there dirty dishes in the sink? If there are, we pick up a dish, wash it, and put it in the drying rack. Come back up here. Are there dirty dishes in the sink? We keep going around and around and around until we reach a point where this is false, at which point we finished washing the dishes and we can leave. Or we can move on to drying the dishes, or we can, whatever our next step is. And so this is a simple example, sort of real world example of this kind of loop. Does that make sense? Questions about that example, about this whole do thing? One thing to notice is the sink example has a nice property in that under plausible circumstances, this loop will end. We will not be stuck here forever. As long as somebody is not bringing more dirty dishes in while we're washing, we will eventually end, because the body of the loop removes a dish from the sink every time. So we reduce the number of things in the sink. And we can't go below 0. There is, it's an integral number of dishes in the sink. We don't have half dishes or quarter dishes or eighth dishes. And we can't have negative dishes. There aren't anti-dishes in the sink. And so we're going to eventually get to 0. And when we get to 0, then this is going to be false and we're done. So this loop has this nice property that we make progress toward the goal of having the sink be empty. Okay. Does that make sense? Questions about that? Now, I'm going to make a new page and we'll talk about what does it mean for something like this to be correct. If a common setup is that we have something Q is true, some kind of setup Q is true, we do some kind of initialization. And we'll look at an example that will hopefully make this more clear. Then we have our loop. And then we want to get to R. So R is our post condition. This is our precondition. And we're trying to prove that this kind of thing is correct. That's the goal, okay? Now, it turns out that presented this way, this is actually nigh on impossible to do. And so what people have found over time is that there's this important idea called loop invariants that make solving, proving the correctness of loops like this a lot simpler. And so if we say, so let me say a little bit about what a loop invariant is, and then we'll try to put it in this context. So P is a loop invariant if say if P is true and B, the guard on the loop, is true, and we do S, P will be true again after S finishes. So formally, that would be P and B as a precondition, followed by S would get us back to P as a postcondition. And that seems maybe a little weird, right? That we'd have this thing and it was true here and we do this and now it's still true again. But like what you're trying to do here is identify some pattern that remains true as you go through the loop, regardless of the particular values that the variables have in the loop. So as an example, let's contemplate a somewhat non-obvious little program. If we say that we've got, we've seen this before, that P is, x equals r times a to the b. Now, let's consider a particular example where we have r starts out being 1, a starts out being 2, and b starts out being 10. So 1, 2, 10. And let's imagine we have this little loop. We have do b greater than 0. And we'll do a complicated loop because, you know, why not? If b is even, we will do the assignment a and b get a times a, and b gets b over 2. Else, we will have r and b get r times a and b minus 1. So that ends the if, and that ends the do. So let's imagine we have this funky little loop, and this is where we're starting. So let's actually just walk through what happens here. So first thing we do is b greater than 0. Yes. So we're gonna do the body of the loop. So then the next thing we have to do is like, well, is b even? And the answer is yes, 10 is even. So we're gonna replace a with a squared. So a is gonna become 4. And b is gonna become b over 2. So this is gonna become 5. And r is gonna stay the same. Nothing changed there. Okay, are we with me? I've said a lot of words, so feel free to be like, stop. Okay, so then we're back up to the top of the loop. Is b still greater than 0? Yes, so we're gonna do the body of the loop again. Is b even? No, so we're gonna do the else statement. So r is gonna get r times a, so that's r is 4. R times a is 4, so that's gonna be the new value of r. B is gonna get b minus 1, so b is gonna become 4, because 5 minus 1 is 4. A doesn't change. Ooh, they're all 4, isn't that pretty? Back up to the top. Is b greater than 0? The answer is yes, so we're gonna do the body of the loop. First thing we check, is this b even? 4 is even, great. So we're gonna, a gets a squared, so that's 16, and b gets b over 2, so that turns into 2, and r doesn't change, so we're down to here. Okay, back to the top of the loop. This is why we have computers, because doing this by hand is boring. Is b greater than 0? Yes, it is. Is b even? Yes, it is. So we're going to square a. 16 squared is 256. This is how you know I'm a computer science nerd. B over 2 is 1. And R continues down in its happy place. Back to the top. Is B greater than 0? Yes. Is 1 even? No. So we do this thing. So R gets R times A. So R times A, 4 times 256 is 1024. No reason why you would know that. And B gets B minus 1, so that's 0. And A doesn't change. Back to the top. Is B greater than 0? No, it is not. It is equal to 0. We are done with the loop. Huzzah! So we've actually completed something. And it turns out that what we've done actually is we computed 2 to the 10th. So how do we know that? Well, this invariant was true every time. If it turns out x ends up being 1024. You can kind of work that out from the last step. So x equals 1024. And it's true that at every line of this, r times a to the b is 1024. 2 to the 10th is 1024 times 1 is 1024. 4 to the 5th turns out to be 1024. Again, no reason you would know that, but you can check it if you want. So 1024 times 1 is 1024. 4 to the 4th turns out to be 256. Times 4 turns out to be 1024. 16 squared is also 256. Times 4 is 1024. 256 to the 1st is also 256. Times 4 is 1024. 256 to the 0 is 1, right? Because anything to the 0 is 1. 256 to the 0 times 1024 is 1024. So this invariant has been true every step through the loop. The numbers have all changed. Excuse me. The numbers have all changed, right? We've been modifying the values in somewhat complicated and not necessarily obvious ways at each step, but at every step, this relationship has held, okay? And it held because I designed this program to make this hold. It didn't hold by accident. Like, this was designed by people to have this property, but it has this property that at every stage, this is gonna still be true. And that's why we talk about it being a loop invariant. It's invariant, it doesn't change, even though we keep going through the loop and modifying the values of the variables in the program. This relationship continues to be true all the way through. Okay? Questions about that? That there's a lot going on there conceptually. Okay? And so we prove, like, let's say we want to prove this whole, well, let's actually finish up the program. If we completely write the program out with all of its pieces, it's going to look something like, if we know B is at least 0, then we're going to do our initialization, which is that R, A, and B are 1. Yeah, so we really just need R as 1 because A and B have values coming in. Let me, R, one more undo. There we go. R is just one. That's the important setup piece. And at that point, that needs to make the invariant true. So it needs to make P x equals R times A to the B true. And now we'll have our loop, do B greater than 0. And now here, we know that the invariance is true and, and the guard is true. Because if the guard wasn't true, we would have never gotten in here. And then we've got our body, if, blah, 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 blah. I'm going to just write that as one big thing. And then we want P to be true after this, odd. So now P is true and the guard is false, so not B greater than 0. That's how we got out of the loop, is the guard had to be false. And that should then hopefully get us to some kind of post condition R. Okay. And so to prove the correctness of this, there's a checklist on page 238. And the three problems at the end of the exam are just straight off the checklist. So for a different loop, actually I should probably write the different loop. But for a different loop, the three problems that we're doing in problem 7, 8, and 9 are just straight off of this checklist. So let me actually, I'm going to skip to a new screen, and we'll actually do this green bit, but we'll do it for the problem that is the on the exam, and then that will hopefully connect a little better to what's on the exam. So on the exam, we have Q is n at least 0, and our initialization step is that X and K get 0 and 0. And we want then P to be true, where P, the loop invariant in this case, is 0 at most K at most N, and X equals the sum over I, 0 at most I less than K, BI. So this is saying X is the sum of the first K elements of this list of values. And K is somewhere between 0 and N. So problem 7 is this. You're starting with Q, doing the initialization, and showing that the invariant is true after the initialization. That's essentially what problem 7 is. And then the loop is do K not equal to N, arrow, and then the step here is that X and K get X plus B of K, comma, K plus 1. Odd. And so here we would have P and K not equal to N, because that's what we know. We know the invariant's true, and we know the guard is true. That's how we got into the loop. And here we would have P. And that is problem 8. Says, if we know P and K not equal to N, and we do this, do we still know P? And so that's problem 8 on the exam. And then the last problem on the exam is showing that the goal R, which is X gets the sum over I, 0 at most I less than N, B of I, that at the end of the whole thing, X should be the sum of the whole list. So it started off being the sum of none of the items in the list, and we add one more in each time through, and at the end, it should be the sum of the entire list. So that last problem says P and the negation of the guard, K equals N, should imply R. And that's problem 9. So we need the things we know when we leave the loop, namely that P is true and the guard is false. That should give us our goal. So this should imply R. And that's where those 3 problems come from. One is this bit, that's problem 7. This is problem 8. And then this is problem 9. So these are the pieces you would need to do most of the checklist on page 238 to prove that this is a correct implementation of a program that adds up all the elements in an array B. You didn't need to understand any of that to do the test. You just do the test and ignore all the stuff I've said in the last 20 minutes. But if some part of what I said in the last 20 minutes made sense, it might help motivate why those 3 problems exist, so they're not just entirely random things that Nick threw at you. But you don't have to understand any of this to do the problems. You can just do the problems and ignore this loop stuff. And now that's fine. So we got like just 2 minutes. Are there any questions about anything in all of this? Questions about the exam? While you're thinking, a reminder to please do course evals. So I think those have to be done by the end of today. So you should have gotten an email with links to how to do course evals for all of your classes, including this one. And faculty really appreciate the feedback. And I know I would, I always appreciate feedback, but I like doubly so in this really weird time. I mean, there is some chance that we end up doing courses online in the fall. I hope that's not what happens. We're all working very hard to not have that be what happens, but Mother Nature is what Mother Nature is, and we may not have a choice in the matter. And so feedback on how things went after we switched to online education, super useful in case I find myself needing to do this again. So yeah, any feedback you've got would be super, super appreciated. So if you have a little time, that would be an awesome, awesome thing. Questions about anything in the 1 minute that are left?
Will this video be uploaded sometime today?
It will hopefully be uploaded in the next hour.
Okay.
It takes sort of 20 minutes-ish for the computer to process it. And then it takes YouTube another 20 minutes to sort of do their stuff. So assuming I don't get too distracted by the world, I'll hopefully have it up before my next class starts. So yes, I will definitely have this up. Actually, I should have, if I've done it right, I should have every video since we went to online teaching up on YouTube and shared on Slack and on the Google Doc. I think the Google Doc might be a day or 2 behind. I'll need to catch that up today. But hopefully we'll have everything. If there's something missing, if you see something's not there, definitely let me know. Because they should all be there, fingers crossed. So, okay, it's 20 after. You have awesome people. You've been super patient under very difficult circumstances. I appreciate your cooperation in all of this. You're awesome folks. Hang in there. Life will return to something resembling normal. And this will be a great story for you to tell your grandchildren or your nephews or something later on. Back in the day, we had the whole pandemic and it was really amazing. So, it'll be a good story. Hopefully things have been okay where you are. Wash your hands and stay safe. And hopefully I'll see a lot of you in office hours next week. Otherwise, hopefully I'll see you in the fall. So thanks a lot. We'll talk to you later. Ciao.
Nick,
Yes.
I have a quick question. I heard rumor tell that we would be on online for fall semester.
That is not decided yet. The president has the president of the whole university system has a couple of working groups that are exploring the situation. My understanding is their goal is to have a decision by sometime in June.
Okay.
So that by some point in June, they will be telling us all whether to expect to be online at the beginning of the semester or not. There are a lot of things being discussed nationally, like every school is having this sort of conversation, and there are a lot of things being discussed. So I know there are schools talking about not having a fall semester at all and just sort of starting over again in the spring, or having fall semester in the spring and then having a really accelerated spring semester next summer. There are people that have talked about having like only first year students come to campus. Um, and all the non-first year students have some sort of structured gap year. I don't think those kinds of like out there crazy things are likely to happen at the University of Minnesota. I think those are things that are more feasible at smaller systems. And the President Gable wants, I think, the whole U of M system to do the same-ish thing. So I don't think that's something crazy like that's going to happen for us. But there are some really interesting ideas being floated about how to handle the fall. There's also always the possibility that we start on campus again in the fall, and it turns out there's then a spike in cases, and they send everybody home again, right? That could happen.
Right.
Hopefully not, but I think you'd have, it would be foolish to pretend that wasn't a possibility, right? We bring students back to campus from all over the state and the nation, possibly the world, although I guess one concern is that international students may have real trouble getting visas to come back. So that could be a concern for international students, but I haven't chased those details down. I don't really know, but that might be a concern for some. But, we bring a bunch of people back to Morris, and that might, lead to a spike in cases, and that could be bad. Maybe we've got good testing, right? Maybe we've got a really solid testing regime worked out, and we can test every student that comes back, and quarantine students that test positive. And so maybe we're like really aggressive about testing as a way of managing the spread once we bring everybody back. I don't know, right? I mean,
Right.
This is all, there's going to be a certain amount of making it up as we go, no matter what people decide. I mean, I guess unless we decide to just keep doing it online, right? Then in theory, we kind of have the summer to figure that out, and we'll be all like prepared and ready to go. And we will have had half a semester of practice. Yay. But anything else is definitely going to be contingent on events. And I guess also it's possible we could start online in August, and by October, things have changed to a point where they're like, we think everybody could go back to campus. Now, whether there be housing, food service would be ready. There's a million questions there. So I kind of doubt we would bring everybody back in mid-semester. But, I don't know. I'm not in charge of all these things.
Right.
So
it essentially, it's just kind of up in the air for now, and we'll figure it out later.
Yeah, and the governor's doing this sort of limited reopening thing, and I think the state and the university are going to very carefully watch the data. Like, what does that do to the number of cases? How does testing and tracking contacts, does that help manage the spread? We get some good news. I think that increases the likelihood we can be back together again in August. If the news isn't great, then I think that lowers the chances. But again, I'm not on these, committees that are making the decisions. I'm just a lowly nothing down here at the bottom of the pile, and I'll do what they tell me. Yeah, I think it's at the moment, everybody just needs to try to be as flexible as you can. And hopefully we'll have some kind of decision in June. But, even if there is a decision in June, trying to be as flexible as possible is still probably a good idea, because there's just so much we don't know about what might happen down the road.
Right. Okay.
I wish I could say I've got a crystal ball and I know exactly what's going to happen, but I don't.
Well, that's fine. I just had heard a rumor, so it's like, well,
No,
better to have more information than just a rumor floating out in space. So
yeah, I don't think I would trust anything like that. I honestly believe that no decision has yet been made. I think there are people working very hard on collecting the data and having conversations. And I think that, people might be leaning certain directions, but I think that the people involved are serious, earnest, smart people who are looking carefully at the data and trying to make meaningful decisions.
Right.
And, and that's got to suck, right? It's a hard job.
Mhm. No, I can't imagine being on that kind of committee right now.
Yeah.
Like, it's almost as if whatever decision you make is the wrong one.
Absolutely. People are going
from
to
the outside looking in. You know?
And anything you do is based on a certain amount of guesswork, right?
Right.
You don't know what the future is going to hold. And so you could be like, well, we should all be online. And then it turns out the number of cases drops and we really get it under control. And then you're like, crap, we could have probably just been back on campus.
Yep.
Or you're like, everybody go back to campus. And then the number of cases spike. And in 2020 hindsight, everybody's like, well, that was dumb.
Yeah.
Right. So, yeah, I'm glad they're paid more than me and yay team and all of that.
Right.
So,
well,
go ahead.
No, you're good, man. I'm out of here. That was my question.
Okay.
Thanks for answering it to the best you could.
Okay. Awesome. You're wonderful people. I got to take off because I've got a student who thinks I'm talking to them in 1 minute. So talk to you folks later.